In this video, I'm going to briefly introduce us to alkyl halides, which in the next few videos after this will lead us into discussions of substitution, so nucleophilic substitution reactions and elimination reactions. So alkyl halides are just alkanes or alkenes that have halogens bound to them. So what we see here, so we have these alkyl halides here where I have the common name up here and then sort of what it's used for right here. So we have the CHCl3 here, which would be the IUPAC name would be trichloromethane. Then we have this here, which is Freon 22, which is a refrigerant. So that's a chlorofluorocarbon. So you see it has a chlorine and has two fluorines on it, so chlorofluorocarbon. Then here we have this 1,1,1 trichloroethane right here. So on the one carbon, there's three chlorines on it, and it's in ethane. So this is used as a cleaning fluid. Then we have this halothane here, which is a non-flammable anesthetic. And so those are just some common examples of alkyl halides. There are also such things as vinyl halides here, which are these alkenes here with these halogens bound to them. So we have vinyl chloride, which is just this vinyl group here with a chlorine bound to it. And so this is actually used as a monomer in PVC, so polyvinyl chloride, which is a type of plastic. And so it can use this double bond here to sort of bond a bunch of these together into a long chain into a polymer. And so that's why it's a monomer of this PVC. Then we have this tetrafluoroethylene, which is a monomer of Teflon. So like the non-stick surface of pans and things like that. And we can have aryl halides, which are just aromatics with halogens on them. So we have this aromatic ring here with these two chlorines on it. So that's paradichlorobenzene, which are used in mothballs. Then we have thyroxine, which is a thyroid hormone. So this has these two aromatic rings here, and it has a bunch of iodines bound to it. And so those are aryl halides. All right, so if we look at the nomenclature of alkyl halides, and I've already kind of been using this throughout, but just to sort of codify what I have been sort of using here. So we want to list the carbon that the halogen is bonded to, and then we use these shortened names. So fluorine, we use fluoro, chlorine, chloro, bromine, bromo, iodine, iodo. And we want to use the prefixes, the di, tri, tetra, penta, and so on when multiple are present. So here are a few examples here. So on this one, this carbon right here has a chlorine bound, so it's 1-chlorobutane. So it has 4 carbons, so butane. So 1-chlorobutane. If it's on the second carbon, then here we'd have 2-bromobutane, for instance. Then right here we have this 3-iodomethylhexane. And so we have this hexane and it has this methyl group on it, but the methyl group is then substituted with this iodine here. And so that's why we put this here in parentheses, because it's like our substituent has its own substituent. And so we always put sort of the nested substituents into parentheses like this. So this right here is an iodomethane, and so we put that here in parentheses, and then that is a substituent on this larger molecule that's hexane, and so it's 3-iodomethylhexane. And so that's how we would name that. If we have this, we have dichloromethane. So if we wanted to draw the stick figure for that, that would be the C right there. So the carbon, then we'd have our dichloro here, and then we'd have our hydrogens like this. And so that's dichloromethane. So of course we have trichloromethane. So that would have the CLs like this. We'd have yet another Cl right here. Then we would have our H like that. So that's dichloro or trichloromethane rather. Then we can have 2-chloro-2-methylpropane. And so we have our propane. So this right here would be one of these methyl groups here, but there is 3 of them, and so we are put like that. So this is our central carbon here. We have this methyl group, and this methyl group right there. So that's our 3 methyl groups, and then we have a chlorine right there, and so that's our 2-chloro-2-methylpropane. So if this right here is our second carbon, this is our 2-methyl, and this is our 2-chloro right there. And so that's how you would name that one right there. And so then we want to talk about like the different halides on here. So we can have primary, secondary, and tertiary halides. And so that just refers to the carbon that they are bound to. So this is a primary chlorine or a primary halide because it's on a primary carbon, where this is a secondary halide, a secondary chlorine, because it's on a secondary carbon. And this is a tertiary halide because it's on a tertiary carbon. And so we just call the things based on what kind of carbon they are bound to. So primary things are bound to primary carbons. For instance, you might see things called primary hydrogens or secondary hydrogens. That's just talking about the carbon that it's bound to. And so that's the sort of way we use of talking about things coming off the carbons, that whatever the carbon is, whether it's primary, secondary, tertiary, the things coming off of it would also be named the corresponding amount there. So the primary halide or secondary halide or tertiary halide. And so that's how we talk about the things coming off of the carbons. We can also have this, so if we're sort of substituted here with bromine, so we have this carbon right here. It has 2 bromines. We call that a geminal halide, where geminus means twin. And so they're both coming off of the same carbon, where if we have them coming off of these adjacent carbons, we call it a vicinal halide, where vicinus is Latin for neighboring, so they're on neighboring carbons, and so we call those vicinal halides. If they're on the same one, they're called geminal halides. All right, so then if we want to look at the halogens here, so we have the electronegativity here. So the fluorine is the most electronegative, then chlorine, then bromine, then iodine. And so that's just that periodic trend. As you go down that column, they become less and less electronegative. And so that's also going to affect the bond length, where things that are more electronegative are going to have shorter bond lengths. And so the carbon to fluorine is the 1.38 angstroms, to chlorine is 1.78, to bromine 1.94, and then to iodine is 2.14. And so we have increasing bond length as we go down that column, the halogens. And then for the dipole moment, we see that the chlorine here actually has the highest dipole moment right here compared to the fluorine, but then we just go down the periodic trend here. And the reason for this flip-flop right here is because the bond length between carbon and chlorine is larger than between carbon and fluorine, and so dipole moments isn't just about the sort of electronegativity difference between them, but also about the bond length. And so between these two, the difference in bond length somewhat overcomes the difference in the electronegativity, where the fluorine is more electronegative than the chlorine, but the bond length between carbon and chlorine is greater than between carbon and fluorine. And so that ends up beating it out, because what we want, so when we calculate it, it's essentially the electronegativity difference, so we can put D like that, times the sort of length of the bond, so the length of the bond. And so In this case, the length sort of ends up beating out the difference in electronegativity. But anyway, if we look down here, so we can look at some of these trends on these alkyl halides here. So you can see I have a few of them boxed here, and that's just because I wanted to show some of these general trends where when we go from fluorine to chlorine to bromine to iodine, we see obviously the molecular weight is going to increase, but we also see that the boiling point increases with it and the density increases with it. And so that's going to be true as we go down this table. So where we're adding more and more to our hydrocarbon chain, but it's always going to be the case, I think pretty obviously, that the molecular weight is going to increase, but we also see that the boiling point is increasing as we go down the halogen column on the periodic table. So that's the physical properties of alkyl halides. So we've already encountered this free radical halogenation. So if we want to look at some of the reactions we can do here with these halogens and the alkyl groups, or the alkanes and alkenes. So like I said, we've already talked about the free radical halogenation, so I'm not going to talk about that too much here. We also have this allylic halogenation, so we can look at allylic bromination, for instance, here. And so this is very similar. So we have this initiation step where we put light on it, and so one of the electrons will go here, one will go there. So we end up with these two free radicals. Then our propagation, we're going to have one of the electrons go here, and then so it's going to come from this hydrogen right here. So one of the electrons will come from there, the other one will end up on there, and so we have this this free radical here, but now we can have this resonance stabilized, so we can have one go there, one come from there, and then this one go right there, so we end up with the free radical right there. And so then this can actually react from either one of these carbons. On here it's not that big of a deal because both carbons are going to be equivalent to each other, but we can see that we can have one of the electrons come from here, so one will go there, one will come from here, and so we end up brominating this right here. So we end up with this right here. So one of these bromines will also be here, so I neglected to put that there. So we do produce another one of those, and that's why it's a propagation step. We can look at what's called allylic shift, and so we can actually put the bromine on either one of these carbons because of this double bond, because of this resonance stabilization. So we can have this radical on that carbon or on that carbon, so it can react with either one of those, and so we can end up with the bromine on either one of those carbons. And so that's what the allylic shift is because of that double bond. It's going to allow for reactions on multiple carbons, and so we can actually get multiple different products. And so I should have probably actually shown this with these two carbons being different. And so say if we didn't have this one right here, so if we erased that one right there, so we don't have equivalent carbons on here, we can get rid of it on these ones as well. So if we just get rid of that carbon there on that one and on this one, we can actually have that ending up on different carbons here. So we can have this ending up on different carbons. So these, if we have these carbons be not equivalent on here, so we could have it end up on that carbon right there, which is that secondary carbon, or we can have it end up on that tertiary carbon. So we could actually have it end up on two different carbons. So that's what the allylic shift is we end up getting, because of that double bond, we can get substitution on two different carbons, so two non-equivalent carbons like that. Because of Zeitz's rule, the one that's going to be more substituted, like this is going to end up being the major product, but we will see this one showing up as well. All right, so we have a few other halogen reactions here. So these are just some very general halogen reactions. So again, we are, well, this is just that radical halogenation right here, but we can also have this right here where we're adding across this double bond where the hydrogen ends up on one carbon right here and the halogen on the other carbon. So we end up with that vicinal halogen. Well, it's not vicinal because this is not a halogen, but they're on these, we're adding to these neighboring carbons across this double bond. This one is where we're making this vicinal halogen right here, where we are adding those halogens across that double bond, so they are on neighboring carbons. We also have this right here where we are replacing this alcohol group here with our halogen, and this one again we're replacing this alcohol group here with this halogen. So this is just a specific example of this general reaction right here. Again, we are adding, well, we're replacing one halogen with another halogen right here. So we're adding this iodine on and removing this other halogen, which is presumably going to be a fluorine, chlorine, or bromine. So this right here is just a specific example of that, where we have this allylic chloride here, and so we add this sodium iodide right here, and so then we are adding this iodine here and replacing that other halogen there. And so what we're going to be talking about in the next several videos are these substitution and elimination reactions. So substitution, there are two mechanisms for that, so the SN1 and SN2. Then the elimination, there are two reactions for that, so the E1 and E2. So the substitution, we're just adding this nucleophile. This halogen here is going to be leaving, so we call it a leaving group, and then we're replacing it with this nucleophile. Then with elimination, we're just we have this halogen and this hydrogen here leaving, and so that particular one is called dehydrohalogenation. Then this base here is just going to be taking that hydrogen, so we have that base to take that hydrogen, and then it extracts that, and then the halogen leaves from here. So that's the elimination right there to produce this double bond. And so these are discussed sort of, within the same chapter in the textbook I'm using, because these are all kind of in competition with each other. And in particular, we'll see that the SN1 and E1 are in competition with each other, and the SN2 and E2 are in competition with each other. But I'll get to that in the videos to come here. All right, so when another atom replaces a halide, the reaction is a substitution. So that's what we have going up here. This nucleophile here is replacing this halogen, or this halide up here, and so that is a substitution. So when a halide leaves with another atom, which is often the H+, which is what we see right here, the reaction is an elimination. And so halogens are good leaving groups, so that's what they're called. They're groups that leave, so they're leaving groups. One of those rare times in chemistry where something is just sort of called what it is. Because the reason that they form good leaving groups is because they form stable anions. And so these halogens are less unhappy to just be this charged anion in solution than a lot of other things. That's why that's why things like HCl and hydrogen bromide and hydrogen iodide make good acids. It's because these halogen anions make really poor bases, and so they are perfectly happy just being negatively charged ions in solution, or at least in polar solutions anyway. But we'll get into solvent effects in the coming videos. But anyway, that was just the brief introduction to the alkyl halides. which is just going to lead us into our discussion on those different reactions, the SN1, SN2 nucleophilic substitutions, and then the E1 and E2 elimination reactions. But anyway, I hope you found this video helpful, and I will see you in the next one.